This video was sponsored by Brilliant. An ant starts at one end of a huge rubber band and starts walking. The rubber band is 10 meters long and the ant walks 1 meter per day. At the end of each day, the rubber band stretches by 10 meters and the ant moves with the stretch. So, after the first day, the rubber band is 20 meters long and the ant is 2 meters from the start. The ant walks another meter during the second day, getting to 3 meters by the end of the day. The rubber band then stretches another 10 meters, growing to 30 meters long, and taking the ant to 4.5 meters. 3 meters out of 20 stretches to 4.5 out of 30. At this rate, will the ant ever reach the end of the rubber band? To answer this question, let's look at a seemingly unrelated topic, the harmonic series. This is the infinite sum, 1 plus a half plus a third plus a quarter, etc. It gets its name from the Greeks, where by listening to the pitch produced by plucking various lengths of string, Pythagoras found that musical intervals correspond to the length of the string plucked. A half-length string produces a note 1 octave above the original note, a third length produces a musical fifth above the octave, a fourth length is the fourth above that, and a fifth length is a major third above that. These intervals are called natural intervals, and although mathematically pretty, it doesn't work well for modern music. So the harmonic series is the sum of all these string lengths. What is the value of the sum? It's infinite, or as a mathematician would say, the series diverges. There's an intuitive way to prove this. Compare the harmonic series with the following strictly smaller series: 1 plus a half plus a quarter, etc. So adding the first 2 terms equals 1 plus a half, the first 4 terms make 1 plus 2 times a half, the first 8 terms make 1 plus 3 times a half, and in general, the first 2 to the n terms make 1 plus n times a half. Notice again that this new series is strictly smaller than the harmonic series. As n becomes large and tends to infinity, so does the sum of the strictly smaller terms, so the harmonic series must diverge as well. We can be even more exact about this divergence. If we add up the first n terms, let's call that h sub n, the nth harmonic number. Now look at the graph of y equals 1 over x from x equals 1 to x equals n. Draw rectangles of width 1 whose upper left corner touches the graph. Notice that the height of these rectangles lines up with the terms from the harmonic series. In fact, the areas of the rectangles are 1 times 1, 1 times a half, all the way up to 1 times 1 over n minus 1. So the total area of the rectangles is simply the n minus first harmonic number. But a little calculus tells us that the area under the curve 1 over x from x equals 1 to x equals n is log of n. This means we can approximate h sub n very well by log of n. With a little more work, h of n is approximately log of n plus gamma. Gamma is an important constant in mathematics, up there with pi, e, and phi. Since log of n becomes arbitrarily large as n tends to infinity, this means that the harmonic series diverges as well. Let's look at some related infinite series. Suppose we thin out the harmonic series so that it contains only the reciprocals of the prime numbers. The divergence of the harmonic series can be used to show that this thinner series also diverges. Moreover, the sum of 1 over p for all primes less than n is approximately log of n for large values of n, similar to our earlier result with the harmonic numbers. What about the sum of the reciprocals of squares of positive integers? This actually converges, and the value is pi squared over 6. Another series is the Kempner series, which is made by removing any term from the harmonic series that contains a 9. Surprisingly, with these terms removed, the Kempner series ends up converging. By now you might see where the original ant on a rubber band problem is going. The first day, the ant travels 1 meter of the original 10-meter rubber band. The second day, the ant travels 1 meter on a now 20-meter rubber band, but this is equivalent to saying the ant traveled half a meter on the 10-meter band. The third day, the ant travels 1 meter on a 30-meter band, but this is equivalent to traveling 1/3 of a meter on the original 10-meter rubber band. So the cumulative distance the ant has traveled by day n is equivalent to traveling 1 plus a half plus a third plus all the way up to 1/n on the original band. But this is the harmonic series, which we know diverges. So the ant will eventually travel 10 meters and reach the end of the rubber band. Equivalently, we know the ant will reach the end of the stretching rubber band since we kept the ratio of distance traveled the same for our calculation. Now the bad news. The number of days needed is the number n such that h sub n equals 10, or roughly log of n equals 10, so n equals e to the 10, a super scary large number. But it works. Have faith in the ant. You know Brilliant for its collection of cool problems and courses. They're guided by principles that we at Tipping Point Math can really get behind. I especially like the principle about cultivating curiosity. You don't have to be a mathematics genius to enjoy these problems. They're easy to grasp, but require insight to solve. Our videos try to do the same, so we heartily endorse Brilliant's philosophy. To learn more about Brilliant, go to brilliant.org/tippingpointmath and sign up for free. And as a bonus to Tipping Point Math viewers, the first 200 people that go to that link will get 20% off the annual premium subscription.